In the previous videos in this module, we've used the rotational kinematic quantities, omega and alpha, to describe the motion of an object moving in a circle. But an object moving in a circle also has a velocity vector and an acceleration vector. In this video, we're going to show that the regular velocity vector and the regular acceleration vector of an object moving in a circle can be related to the object's angular velocity. To start, let's suppose that this blue dot here represents an object moving along the circle. Let's say that the blue dot starts here and then moves over to here. Let's say that as the blue dot moves along this portion of the circle, it sweeps out an angle delta theta. Let's say that the radius of the circle is r. Let's also say that the arc length swept out by the object as it moves from here to here is delta s. So delta s is the arc length swept out by the object. If you're not familiar with the idea of arc length, imagine that we take a piece of string and lay that piece of string exactly over this arc of the circle. If we then take the piece of string and pull it tight, then the length of that string when we pull it tight is the arc length. You may recall from your trigonometry classes that the subtended arc length is equal to the radius of the circle multiplied by the subtended angle. This equation is only true if the subtended angle is measured in radians. Let's also suppose that the time needed for that object to get from here to here is delta t. Now let's take this equation over here and divide both sides by the time it took the object to get from here to here. We'll have delta s equals r delta theta. Now divide both sides by the time interval. Now what do we have over here on the left side of the equation? Well, this is distance over time. This would be the speed of the object. Then we have the radius of the circle. And here we have delta theta over delta t. This would be the angular velocity of the object. So for an object moving in a circle, we have that the speed of the object is equal to the radius of the circle times the angular velocity. So this is our first equation, which relates a rotational kinematic quantity, in this case omega, to a linear kinematic quantity, which in this case is the speed of the object. Now I'd like to address a different question. Let's say we have an object moving round and round the circle at constant speed, not getting faster or slower. If we have an object moving round and round the circle at constant speed, not getting faster or slower, can we say that the object is accelerating? To answer that question, first of all, what is the acceleration? The acceleration is the rate of change of the object's velocity vector. So if the object's velocity vector is changing, then the object is accelerating. So let's have a look at this. So my fingers are going to go round and round a circle again, and I'm going to use this pen to represent the velocity vector of my fingers. As my fingers go round and round the circle at a constant speed, is their velocity vector changing? You can see that the velocity vector is changing because the direction of the velocity vector keeps changing. When my fingers are at this position on the circle, the velocity vector is pointing like so. When my fingers are at this position on the circle, the velocity vector is pointing like so. The velocity vector did change. It went from pointing this way to pointing this way. So an object moving in a circle at constant speed is, in fact, accelerating. So now we ask, what is the acceleration vector for an object moving in a circle at constant speed? There are two parts to this. First, we would want to know the direction of the object's acceleration vector. And second, we would want to know the magnitude of the object's acceleration vector. First, let's talk about the direction of the acceleration vector. Let's think about an object going around the circle at constant speed, and let's think about the moment just as the object is rounding the top of the circle. Just before the object gets to the top of the circle, the velocity vector is pointing this way, and just after the object passes the top of the circle, the velocity vector is pointing this way. So what is the change in the velocity vector of the object as the velocity vector goes from pointing this way to pointing this way? Notice that as the object goes from here to here, the velocity vector goes from pointing left, but a little bit up, to pointing left, but a little bit down. So watch carefully. What is the tip of the velocity vector doing as the velocity vector goes from this position to this position? Can you see that as the velocity vector goes from this orientation to this orientation, the tip of the velocity vector is moving downward, like that? We can see then that as the object rounds the top of the circle, the velocity vector changed from being a little bit upward to a little bit downward. In other words, the change in the velocity vector is downward. So right as the object is rounding the top of the circle, the change in the velocity vector is downward. And so the acceleration vector of the object, which is there to describe changes in the velocity, points downward. We can repeat this analysis at any other point on the circle, and we will see that in each case, the acceleration vector will point in towards the center of the circle. The acceleration vector of an object moving in a circle at constant speed is called a radial acceleration because the acceleration will always point in along a radius towards the center of the circle. So I'm going to call these acceleration vectors a sub r for radial acceleration. So the radial acceleration describes the change in the direction of the velocity vector. And it always points to the center of the circle. So now we figured out the direction of the acceleration vector for an object moving in a circle at constant speed. The next question is, what is the magnitude of that acceleration vector? The magnitude of that acceleration vector depends on a couple of different factors, so I'm going to do some demonstrations here to show you why that is. In the first demonstration, I'm going to have an object move at a constant speed around a small circle, and then I'm going to have that object move at the same speed around a bigger circle. So here's an object moving around a small circle at a particular speed, and notice that I'm using the pen to describe the velocity vector of the object as that object continues to move around the circle. Now let's say I have that same object move around the bigger circle at the same speed that it was going around the smaller circle. Does the velocity vector swing around more rapidly when the object moves on the small circle at that particular speed? Or does the velocity vector swing around more rapidly when the object moves around the big circle at that same speed? So clearly, the velocity vector is swinging around more rapidly as the object moves around the small circle at that fixed speed. Okay. So since the velocity vector changes more rapidly for the object moving on the smaller circle, we're going to say that the acceleration of the object is inversely proportional to the radius of the circle it's moving on. Okay, now how does the acceleration of the object depend on the object's speed? To show that, I'm going to have the object move around the larger circle twice, First, the object will move around the larger circle slowly, and then the object will move around the larger circle more rapidly. Okay, so here's the object moving around the larger circle slowly, and look at the rate at which the velocity vector swings around. Okay, now here's the object moving around the larger circle rapidly, and look at the rate at which the velocity vector swings around. Can you see that the velocity vector swings around more rapidly when the object is moving faster, and the velocity vector swings around more slowly when the object is moving more slowly? Since the velocity vector swings around more rapidly when the object is moving faster, the acceleration must be greater when the object is moving faster. And now here, we're tempted to say that the acceleration is proportional to the speed of the object, but it actually turns out that the acceleration is proportional to the square of the speed. If we put these two things together, we can get a formula for the magnitude of the acceleration for an object which is moving in a circle at constant speed. The magnitude of that acceleration is the square of the speed divided by the radius of the circle. We can get another formula for the radial acceleration by combining this result with our earlier result, which relates the speed to the angular velocity. So I'm going to take this and copy it up to here. So we have radial acceleration would be speed squared divided by radius. Let's box that one. That's an important equation. To get an alternate expression, let's take this result, v equals r omega, and substitute into the numerator here. That would give us AR equals omega r quantity squared over r, which becomes omega squared r squared over r. So notice that r squared over r just becomes r. And now we have a second formula for the magnitude of the radial acceleration, namely it is omega squared r. To sum up, in this video, we have learned several equations which describe the velocity and acceleration of an object moving in a circle. First, the speed of the object is equal to the radius of the circle times the angular velocity of the object. An object moving in a circle will always have a radial acceleration which points to the center of the circle. The magnitude of the radial acceleration can be expressed as the square of the speed divided by the radius of the circle, or the magnitude of the radial acceleration can be expressed as the square of the angular velocity times the radius of the circle.